All right, guys, lecture 14, part 2. Hopefully there will be 3 parts. Might even be 2 parts if I just kind of push on and hope the thing records. So this is a continuation where we started yesterday. And yesterday we talked about addition and subtraction of complex numbers. And today I want to talk about, guess what? Multiplication and division. Okay, so this is pretty straightforward, I think, I hope. So I'm going to talk about complex multiplication. And I'm going to do it in general terms, if I could, just for the laugh, and then maybe do an example, just to show you what's going on. In general terms, if you've got if you've got two complex numbers, z1 x1 plus I y1, and z2 is equal to x2 plus I y2, and you want to multiply them together, z1 by z2, then you just use the ordinary rules of algebra, right? So you've got x1 plus I y1 times x2 plus I y2. And you remember from national school when you're doing this algebra stuff, when you introduced it, is that what you do is you multiply each term in the second brackets by each term of the first bracket. So what you get then is you just get x1 into x2 plus I y2 plus I y1 into x2 plus I y2. And you multiply out, so you get x1, x2, plus I x1 y2 plus I y1 x2. And then you have to be careful here, so you get I by I, which is I squared, plus I squared. Sorry, the pen is just gone to the hills. So you get I squared y1 y2. Okay, so that's an I squared. And I squared is minus 1, so what you end up with then is x1, x2 minus y1, y2 plus I into x1, y2 plus y1, x2. And then you can do all that stuff, you know, if you want to get the conjugate of z1, z2, it's just exactly the same with this plus change to a minus. If you want to get the real part of z1 multiplied by z2, it's just x1, x2 minus y1, y2. And then if you want to get the imaginary part, it's just this bit. Okay, so that's what it is. So let me just do an example. It's just I multiply 3 minus 2i by 4 plus I. So you 3 by 4, which is 12, plus 3i. So I'm multiplying the second bracket by the 3. Then I'm multiplying the second bracket by the minus 2i. So you get minus 8i minus 2i squared. And you have to be a little bit careful, as I said before, about the minus sign of complex numbers. I squared is minus 1. So minus 1 by minus 2 gives you plus 2. So what you end up here then is 14 plus or minus 5i. Okay. And if we're asked for the conjugate of this, then it would be 14 plus 5i. The real part is 14. The imaginary part is minus 5. Boom, boom. Now, there's one very, very important multiplication that I want to talk about, just because it is very, very useful. It's not very useful; it's very kind of important. So it's one to do with the complex conjugate. So if you multiply z by its conjugate, what do you get? So let z be x plus iy. Now I don't need an x1 and y1 here because I've just got one complex number z. So if z is x plus iy, x bar is x minus iy. Sorry, guys. If I multiply that out there, I'm going to get x squared. And then minus I xy. And then here I'm going to get plus I xy. And then minus I squared y squared. Now you're very young and you're idealistic and you're very hopeful, and why should you not be, I suppose? But there's nothing better, folks, than cancellation in life. This is just the best thing that ever is going to happen to you in life. And here, look, you see cancellation: minus I xy plus I xy. These will cancel, and I squared is equal to minus 1, and minus 1 gives you plus 1, so you get x squared plus y squared. And that's a really important little result. If you multiply z by z, its conjugate, you get x squared plus y squared. And remember what x is. X is just the real part. and y is the imaginary part. So z bar is the real part squared plus the imaginary part squared. Boom, boom. It's an important little result. So for example, if I multiply 1 plus 5i by 1 minus 5i, you don't have to do it. You don't have to multiply it out. You can multiply it out, but just to save time, what you would do then, okay, so these are conjugate of each other. So it's just 1 squared plus 5 squared. And that's just 26. That's it. So this happens not often, but it's an important idea. And this idea of z bar equal x squared plus y squared, we're going to be using in a second now for something else. So it is kind of important. And finally, folks, excuse me, what we're going to do, we did addition, subtraction, multiplication. Now I want to talk about division. I do it by means of example, I suppose. I could do it in general like I did here. You know, I could do it, but it gets a little bit messy, but you can do it, and that's fine. And maybe I should do it in general, and then just give you an example. But I'm just going to give you an example first to bring you back into your happy days in secondary school, where you had a school and you had schoolmates, you could go into school and learn stuff. Yeah. So listen, let's talk about 1 plus 2i divided by 2 minus 3i. So here we've got one complex number divided by another, and we want to do that. Now, the way you do this, and it's not obvious at all that this is what you do, but I don't know if you remember this from secondary school, but you can you multiply above and below by the same thing. So I can, if I've got an expression here and I multiply it by something over something, I don't change the expression. So here what I'm going to do the multiplication, and there's a reason why you do this, as we'll see in a second. You multiply above and below by the conjugate of what's below. And what's below here, the denominator is 2 minus 3i, and the conjugate of that is 2 plus 3i. And the reason why you do that is because people have found that this maybe works. So maybe we should do that. And if you look at the top, then what you get is you just get 1 plus 2i by 2 plus 3i. But below the line, you'll see, look, this is the conjugate of each other. These two are conjugate of each other. So when you multiply this by this, you get 4 plus 9. You get 2 squared plus 3 squared. And that's the reason why you multiply above and below by the conjugate, because you know what's going to go below the line is going to be a real number, which is nice. Okay? In complex numbers land, when you get a real number below the line, that's good. So then you multiply above the line, and you get what you get. You get 2 plus 3i plus 4i plus 6i squared all over 13, right? Because I just multiplied out here 2 plus 3i plus 4i plus 6i squared, and I squared is minus 1, so you get minus 4, because minus 6 plus 2 is minus 4, plus 7i over 13, and then you can write that then as minus 4 over 13 plus 7 over 13i. So the reason why you multiply above and below by the conjugate is that you end up with a complex number. Because remember what a complex number is. It's a number plus another number times I, which is exactly what we have here. So this took people a while to figure out. This is not an obvious thing to do, but this is what you do. And so the real part here is minus 4 over 13, and the imaginary part is 7 over 13. So there you are. So that's division. So boom, boom. We've done a lot now, right? When you think about it, we've got addition, subtraction, multiplication, division. And what else could there be? And surprisingly enough, there is a lot more to complex numbers. One of the things that I want to talk about very quickly, actually, is this idea of plotting a complex number. Because if you look at the complex number, this complex number here, there are two parts to it, right? There's a real part and there's the imaginary part, and there are two numbers. Now, whenever you have two numbers in mathematics, and in engineering mathematics in particular, you should always start thinking about plotting. Okay, plotting points on an x-y axis is really, really useful, because it gives you a picture of what the numbers are doing, and it's an easy way of summarizing what's going on. So in this case, we've got two parts to every complex number, so we can plot each complex number as a point in the xy plane. So so maybe we just do that. So let's plot 2 plus 3i. Now the way you do it, guys, you change the x and y axis. You call the x-axis the real part of z, and you call the y-axis the imaginary part of z. Now, the y-axis is the imaginary part of z, folks. It's not I times, there's not 1i, 2i. It's the imaginary part of z. So in this case, you see it's 2 along the real axis and 3 along the imaginary axis. So you get that point there. All right, so that's no big deal, really, I suppose. But it's a nice, useful way, especially if you have a lot of complex numbers and you want to see what the relationship between the complex numbers is, or the relationships are between the different types of complex numbers that you have. If you plot them, you can sometimes see a pattern, which is sometimes good. Patterns are good in mathematics. So there you are. So this is plotting a point. So that's pretty straightforward. And this is called an Argand diagram, if you want the technical term, although why it should be called something is because it's an obvious thing to do, especially as an engineer. You've got two numbers associated with each other. You plot them. That's the response we're looking for. But if you look at, when you start plotting it, then you see there's other things that suggest that there's another thing that suggests itself to you, or should do automatically, and that's to do with the relationship of the point to the origin. So if you look at the origin here, what the complex number is telling you to do, or this form of the complex number is telling you to do, is to go 2 along here, and then when you get to here, turn the corner and go up 3 along here. So this is what's called, I'm going to just talk to you now about the terminology. This is called the Cartesian form of a complex number. There is another form which we'll talk about maybe tomorrow, but there is this, it's called Cartesian form. And what the Cartesian form tells you very explicitly actually is how many steps you must take along the real axis and how many steps you must take along the imaginary axis to get to the point. Now, if you're at the origin, that's certainly one way to get to, from here to here, is to go along here and up here. But I would suggest to you that maybe a more obvious way to get from here to here is to go directly from the origin to the point. And when you do that, then you're introducing this whole notion of polar coordinates, which are really important, especially if you're a mechanical engineer. So a polar coordinate has 2 coordinates, and the 2 coordinates are this angle here, which we're going to call theta, and this distance along the line here, which we're going to call r. So very importantly, folks, really importantly, theta should be given, you should use radians for theta. Get into the habit now of using radians, although sometimes I will give you the angle in degrees, but that's really bad. I should give it to you in radians. So get into radian mode, especially when I'm asking you to answer a question as to what the angle theta is. I'm expecting you to give me the angle in radians. So that's the very first thing. So this is radians, please. Very important, you're engineers now, you're not nursing students or journalism students. So engineers use radians. The angle theta, you can call it, this is the terminology, it's called the angle. You can call it the angle if you want to. Or in complex numbers, it's usually called the argument. And that's probably the one I'm going to use, the argument. But you can call it the angle if you want to. Or it's going to be, it's a distance, so you can put in centimeters and meters, whatever units you want. It's called the radius, I suppose. But or it's also called, and this is the one we're going to be using, the modulus. So they're all equivalent. So you can either use the radius of the complex number if you want to, that's fine, or the radial distance or something, that's fine as well. But we're going to usually talk about that distance there as the modulus of the complex number and the angle as the argument of the complex number. Now, why there's different terminologies for the same thing is just historical. There's a historical reason. That people didn't interact with each other as we do now. So maybe interaction is bad as the virus thing is shown. But we're going to be using the modulus as our term for the distance, and we're going to use the argument as the term for the angle. Now, boys and girls, to get in this case, let me just do it in this case first. If you look at r, this is a right angle triangle, right? And this distance here is 3, this is here 2. So by Pythagoras, we get r squared is equal to 2 squared plus 3 squared. And so we get 13. 4 plus 9 is 13. So or then is the square root of 13. It's not plus or minus the square root of 13 as it usually is in mathematics, but it's plus square root of 13 because or is a distance and must be positive. You cannot have a negative distance. It doesn't make sense. Okay, so or is the square root of 13. And actually, if you think about this, guys, if you look at this thing here, 2 squared plus 3 squared, that's the real part squared, the imaginary part squared. In general, I'm going to give you a look at it. Wait till you see this, guys. R squared is z by z bar. Whoa, this is just a little rule here. Or then is the square root of z bar. What do you think? Yeah, that's kind of, you don't really need that. That's just, in general, that's what or you can do. That's another way of calculating or. Usually, the way I ask you this in the exams, I give you a point and ask you to calculate or, and you just take r squared as this, or you can just take r as the square root of the real part squared plus the imaginary part squared, as you would here. Okay, that's fine. Now, the calculation of the argument of a complex number is tricky, I think. All right, it's not. I don't think this is easy, actually. And if you look at textbooks, textbooks gloss over this and pretend that it's not difficult. Now, maybe this could be just me, that I'm the only person on the planet who finds this a little bit not obvious, but it's not obvious, I think, to calculate the argument of a complex number. You have to be a little bit careful. If you're up here in the first quadrant of the xy plane, it's relatively straightforward, okay? So for here, for instance, we know that tan of theta, I'm going to come up here, is 3 over 2. Okay? So therefore theta then is tan inverse of 3 over 2. Now theta is the angle made by the line and the positive direction of the real axis. So when you're in the first quadrant, there's no problem. This angle theta is fine. It's this angle here, that is fine. But if you're anywhere else, if you're in the other 3 quadrants, you just have to be a little bit careful. So if you're in the first quadrant, there's no problem. And you're in the first quadrant when the real part is positive and the imaginary part is positive. And then you just draw your triangle and you just use ordinary trigonometry. Tan theta is 3 over 2, and then theta is tan inverse of 3 over 2. Make sure you're in radian mode when you calculate the tan inverse of 3 over 2. You do not want it in degrees, you want it in radians. All right, guys, I'm going to stop here, and then I'm going to come back and talk about the argument again, because I want to make sure that I'm recording this, and then I'm going to do a little bit more on the argument, and then we're going to stop, and that will be the end of lecture 14. All right, talk to you soon. Bye.